All right, so let's look at movement of substances across the plasma membrane. So two main ways in which we move substances across the membrane. One is using energy and one is without. So the first is without, and these are called passive mechanisms. So moving substances across the plasma membrane without using energy. So the first one you're probably familiar with, this is called diffusion. This is a movement of substances from areas of high concentration to areas of low concentrations. So, if we, sprayed some air freshener, you can smell that air freshener in other parts of the house apart from the area that you first initially spread. Okay? So this is showing some salt crystals getting spread around in water. All right? Now, diffusion is caused by the random motion of molecules and their collisions. So what's occurring here is just like the beginning of a game of pool. So in the beginning of a game of pool, you take all the balls and you put them into a rack, and you hit into that rack with a cue ball, which hopefully spreads the balls throughout the table. All right? So that's what's occurring microscopically here. So these salt crystals are all together, water molecules are banging into them because the water molecules are constantly moving, and it's going to spread these salt crystal molecules apart. And so when they get spread apart, well, the water molecules bang into them, spread them apart even further, and so on. So it's really the collisions here which spreads the molecules apart. All right? And eventually, concentrations are going to equal out, or we're going to reach an equilibrium. And so what I mean by that is, if I took a sample here, or here, or here, or anywhere in there, I would find the same number of salt crystal molecules to water molecules in there. Okay? So, what can diffuse through membranes? Well, I kind of mentioned this earlier. So small hydrophobic molecules are the only things that can diffuse through. Okay? So, when we're talking about that phospholipid bilayer, water-soluble things cannot go through. Only lipid-soluble stuff can, all right, or hydrophobic molecules. But what's an important role in this is oxygen and carbon dioxide can simply diffuse through membranes. So when we inhale oxygen, it simply diffuses from the air in our lungs into our blood, and carbon dioxide is going to diffuse in the opposite direction. All right? Now, if you're a molecule that cannot go through the membrane, well, you might need some help, and this is what is known as facilitated diffusion. So this is diffusion by means of a transport protein, either using a channel protein like so, or using a carrier protein. And these are for large and hydrophobic molecules. Okay, so you can see, lipid-soluble molecules can't go through, lipid-soluble can. All right, so this is showing small molecules moving through a channel protein. Here is showing glucose moving through a carrier protein, which I kind of talked about before. Another way that we can move molecules through membranes is what is known as filtration. So filtration is a movement of substances through a membrane as a result of hydrostatic pressure. All right? So this occurs in our capillaries, which are our smallest blood vessels. So if we go from a larger blood vessel to a smaller blood vessel, what's going to happen there is each time we go from a larger blood vessel to a smaller one, we increase the hydrostatic pressure in those tubes. All right? So all we do is make the opening smaller. If you've ever played with a garden hose and you stuck your thumb over the end of the garden hose and the water just sprays out, you're making the end smaller, which increases the hydrostatic pressure there. All right? So by the time we get to our capillaries, here, every time we've gotten to a smaller blood vessel, hydrostatic pressure is increased, blood pressure at this point, right? And so by the time we get to our capillaries, our smallest blood vessels, here the hydrostatic pressure is so high it's going to force water and small dissolved substances through those membranes. All right? Large molecules, like plasma proteins, blood cells, stay in the blood. They're too large to move through those membranes. All right? So that's filtration. So the last passive mechanism is known as osmosis. This is a movement of water across the semipermeable membrane from areas of low concentration of solids to areas of high concentration of solids. All right? And a solute is a part of a solution. A solution is a mixture of two or more substances. So a solute is a dissolved substance. All right? And a solvent is a substance that does the dissolving. All right? So an easy example of a solution is Kool-Aid. So you take Kool-Aid, you take the water, you mix into that water, Kool-Aid mix, and the sugar, you stir it up. So the Kool-Aid mix and the sugar are solutes, whereas the water is the solvent, things dissolve in there. And water is the solvent of life. We dissolve things in water in our cells and in our body. All right? So if we go back to the definition here, what I'm saying here is water is going to move from areas of low concentration of dissolved substances to where we're going to have more dissolved substances. And this is trying to show this here. We have more dissolved substances in here than outside, so water moves into that tube to try to equal out concentrations. Here's another example here. We have a lot of stuff here, none over there, so water shifts to equal out concentrations. All right? In osmosis, here the solvent moves to equal out concentrations. Where in diffusion, the solid move to equal out concentrations. All right? So the end result is still the same. We're still going to reach an equilibrium. All right? So what I'm saying about this is water is going to shift in your body between your cells, your blood, and other areas, these interstitial fluids, which are between the cells, due to osmosis and also due to filtration processes. All right, so now we can look at this in terms of what water is going to move in terms of dissolved substances within our cells. Now, there are three situations. One is known as an isotonic solution. Iso means same, all right? So this is a solution with the same solid concentrations as body fluids. So if we take a red blood cell, or any cell, and we put it into an isotonic solution, which, oh, by the way, is a 0.9% salt solution, there will be no net movement of water. So this is trying to show water goes into the cell, water leaves the cell, it's just the same amount of water entering the cell as the same amount that leaves. This is what a red blood cell looks like in an isotonic solution. Okay. Next is a hypertonic solution. So a hypertonic solution, so if you're hyperactive, your activity level is above normal. So a hypertonic solution is a solution that has a higher concentration of solids than cells. All right. So this is above a 0.9% salt solution. And so in this case, water will leave the cell to try to equal out concentrations within the cell and outside. So more dissolved solids outside the cell than within the cell. Water leaves the cell to equal out concentrations. All right? So if you've ever been to the ocean, right? Oh, so the cell will shrink because water leaves. So if you've ever been to the ocean and tasted the ocean water, you'll notice it's very salty. It's anywhere from 2.5 to 3% salt solution. So it's a hypertonic solution. If you ever heard that if you drink ocean water, you can become dehydrated from this. And the reason is, instead of you ingesting that water into your digestive tract and then absorbing it into your body, what happens is you actually lose water from your body to your digestive tract, and then you're going to end up pooping that out. So if you continue to drink ocean water, you will die of dehydration due to diarrhea. Not a pleasant way to go, and that's all due to osmosis. All right? Next is a hypotonic solution. If hyper is above, hypo means below. So this is a solution with a lower concentration of solids and cells. So it has less than a 0.9% salt solution. So if you take a cell and you put it into a hypotonic solution, what will happen here is that water will enter the cell to try to equal out concentrations because there's more dissolved solids in the cell than outside. Okay? And so the cell will expand. And a lot of times these textbooks will show red blood cells here exploding. And this will happen to a red blood cell. You take a red blood cell, you put it in a hypotonic solution, and it will, so much water will enter it that it will explode. All right? But how often do you think red blood cells are exposed to a hypotonic solution? Well, only when you take red blood cells out of our body and put them into a hypotonic solution. Because I'm going to tell you, most of the stuff that we drink is hypotonic solutions. Fresh water is a hypotonic solution. All right, so all the lakes, streams, ponds around us. Water out of the tap water is hypotonic. Anything that you drink is hypotonic. That's how we absorb the water from it, is it has to be hypotonic. So as you notice, if you've ever tasted ocean water, it doesn't taste great. All right, isotonic water still doesn't taste great. That's a saline solution that you put your contacts in. If you ever tasted your tears, that's an isotonic solution as well. We typically avoid isotonic and hypertonic solutions. We like the taste of things that are hypotonic because we can get the water from those things.